A mountain can look still while the system beneath it stays active, layered, and hard to read. Mount Shasta is one of those places. How many melt-rich pockets can sit beneath a volcano that has not erupted in thousands of years? How deep are those pockets? And how much warning would the surface give before the plumbing below started to shift? The latest work around the Cascade Arc, combined with earlier studies focused directly on Shasta, points to a subsurface system that is more complicated than a single underground reservoir and more persistent than a simple snapshot of dormancy might suggest. Mount Shasta is not a minor cone on the volcanic map of the West. The U.S. Geological Survey describes it as the most voluminous of the Cascade Range volcanoes, rising to 4,317 meters or 14,163 feet, and standing about 97 kilometers or 60 miles north of Redding. It is classed as a stratovolcano, and the USGS gives it a very high threat potential. That rating does not mean it is erupting now. It does mean the volcano remains part of an active volcanic system that deserves close attention, especially because past eruptions, landslides, and mudflows have left a long record around the mountain. The usual shorthand for a volcano's hidden interior is the word magma chamber, but the science is rarely that neat. The USGS explains that magma can connect through cracks and linked storage areas beneath a volcano, which means the subsurface can behave as a network rather than a single tank. Mount Shasta's own research history supports that picture. A diffusion chronometry study of primitive magnesian andesite from Shasta found evidence that magma storage, mixing, and crystallization occurred at about 500 megapascals, or roughly 15 kilometers, before eruption. The same work concluded that ascent from that depth could happen in years, while the wider edifice took place through repeated pulses over hundreds of thousands of years. That is where the idea of multiple magma pockets becomes meaningful. It does not necessarily imply a single giant cavity under the mountain. It points instead to separate storage levels, brief staging zones, and melt-rich regions that can be activated at different times. The Mount Shasta study from 2022 concluded that the primitive magnesian andesite preserved evidence of a more complex history than a direct, uninterrupted rise from the mantle. It describes storage in the middle crust, mixing, and then ascent through the upper crust before eruption. In practical terms, that means some magma can pause, crystallize, and mix before it moves again, creating a layered underground system rather than a one-step pipeline. A separate, broader study of the Cascade Range published in Nature Geoscience in early 2025 added a regional frame to that picture. Using seismic imaging of scattered waves, the researchers reported low seismic velocity bodies indicative of partial melt between 5 and 15 kilometers beneath most Cascade volcanoes. That work matters because it suggests persistent magma bodies can remain in place even where the surface has been quiet for a long time. At the same time, the same study noted that Mount Shasta had poor azimuthal coverage, which limits how cleanly its interior could be resolved in that dataset. In other words, the regional result strengthens the case for long-lived magma storage in the Cascades, but Shasta still needs its own sharper imaging to pin down the details. That limitation is one reason the Mount Shasta story is not a simple headline about a newly discovered chamber. It is a story about converging lines of evidence. Older petrologic work, newer diffusion studies, and broader Cascades-wide imaging all point in the same direction. The crust beneath Shasta is capable of storing melt at more than one level. A 2023 synthesis paper on magma storage along the Cascade Arc also noted that low seismic velocity anomalies beneath Mount Shasta had already been interpreted as possible crustal magma reservoirs, while cautioning that data coverage and resolution vary from volcano to volcano. That kind of caution is important because a magma body that is detected by chemistry may not look exactly the same in seismic data, and a seismic anomaly may not tell the whole petrologic story. The monitoring record adds another layer of context. The USGS says Mount Shasta currently has 9 GPS receivers in its geodetic network and 12 seismometers in its seismic network, both of which feed real-time monitoring. The same USGS volcano page reports that earthquake activity has been low for decades and that ground deformation is negligible. That combination matters because it separates long-term magma storage from immediate unrest. A volcano can contain melt at depth without showing the rapid signals that usually accompany an eruption on human timescales. For the moment, Shasta appears to fit that pattern, a system with a lively geologic past, a hot interior, but no current sign of accelerating deformation or sustained earthquake swarms. The eruption history helps explain why scientists keep watching it. The USGS says the youngest dated eruption occurred about 3,200 years ago, and the record over the last 10,000 years suggests an average eruption interval of roughly 600 to 800 years. That does not mean eruptions arrive on schedule. Volcanoes do not obey calendars. It does mean the mountain has erupted many times in the geologically recent past, including episodes that produced block and ash flows, lava flows, domes, and mud flows. The same USGS material notes that Mount Shasta began forming on the remnants of an older volcano that collapsed hundreds of thousands of years ago, an event that helped create one of the largest landslides known on Earth. For the public, the key point is not that Mount Shasta is about to erupt. It is that the mountain remains active in the geologic sense, with storage zones that appear to have lived through repeated episodes of crystallization and recharge. The 2022 Shasta study suggests that some primitive magma may rise through the crust relatively quickly, while the bulk of erupted andesitic and dacitic material may need thousands to tens of thousands of years to assemble. That kind of timescale points to a system that is constantly reorganizing below the surface, even when the top of the mountain seems calm. The broader scientific implication is that the crust beneath a large Cascade volcano can hold more than one magma pocket at once, not as a dramatic exception, but as a normal part of volcanic architecture. Some melt may sit deeper, some may pool in the mid-crust, and some may be stored closer to the surface before eruption or freeze up. That layered behavior is exactly why Mount Shasta keeps appearing in the scientific literature. The mountain is large, active in the geologic record, and still only partly resolved by modern instruments. The next step is not to assume a single hidden chamber. It is to understand how many pockets exist, how they are linked, and which ones matter most when the system starts to change. Mount Shasta sits in a volcanic arc built by subduction, and that setting helps explain why the magma system beneath it can be so layered. In the Cascades, the Juan de Fuca plate descends beneath North America, carrying water and altered rock down into the mantle. That water lowers the melting point of the overlying mantle wedge, helping generate magma that can rise into the crust. The USGS notes that Mount Shasta's composition is mainly andesite and dacite, which are the kinds of magmas commonly associated with more evolved storage and differentiation in arc volcanoes. The result is a volcano that is not simply fed from below once and left alone, but repeatedly replenished, mixed, and reorganized as new melt arrives. That chemistry is one reason Mount Shasta has attracted so much petrologic attention. Earlier studies cited in the Mount Shasta literature describe primitive basalts and andesites from the region, high magnesian andesite, and contrasting water-rich melt inclusions, all of which point to complex magmatic processing rather than a single straight path from mantle to eruption. The 2022 diffusion study pushed that logic further by tying magma evolution to time. Storage at about 15 kilometers, mixing less than 10 years before eruption, and ascent rates fast enough to move melt through the crust in years rather than centuries. That is the kind of evidence that turns a volcano has magma into a volcano has a system of linked storage pockets at different depths. Recent regional imaging reinforces that point even where the individual volcano signal remains incomplete. The 2025 Nature Geoscience study found low seismic velocity bodies under most Cascade volcanoes at roughly 5 to 15 kilometers depth, a range that overlaps the depths inferred from Mount Shasta petrology. The author's caution about Shasta's poorer station coverage is useful, not a weakness to dismiss, because it shows the limits of current maps. A volcano can be active and magma-rich without being imaged cleanly. In Shasta's case, the seismic and petrologic clues appear to be converging on a multi-level crustal system, but the exact geometry is still being refined. The practical value of that refinement is straightforward. If magma storage is distributed across multiple pockets, then eruption forecasting has to account for more than a single full chamber. It has to watch for changes in deep melt supply, mid-crustal recharge, gas release, deformation, and earthquake patterns that may reflect one pocket becoming connected to another. The USGS already tracks the mountain with GPS and seismometers, and it also reports that hot springs and volcanic gases still seep from the summit, a reminder that the system remains thermally alive. Those surface expressions do not predict an eruption on their own, but they do fit a volcano whose interior has not fully cooled. The hazard summary on the USGS Mount Shasta page says future eruptions like those of the last 10,000 years would probably produce ash, lava flows, domes, and pyroclastic flows, and could endanger infrastructure within several tens of kilometers of the volcano. That is a broad hazard statement, not a forecast. It reflects the fact that the mountain has produced different eruptive styles in the past, and that its steep slopes, snow and ice, and loose volcanic deposits can turn even moderate activity into downstream hazards. Mud flows have repeatedly affected stream channels in the last 1,000 years, and that part of the risk matters even if an eruption is not especially large. The mountain's history also shows how quickly a long, quiet system can still retain a ready magma plumbing network. The USGS notes that the youngest dated eruption was about 3,200 years ago, and that the average recurrence over the last 10,000 years is on the order of centuries. That does not make the volcano predictable, but it does show that long repose intervals are not the same thing as extinction. For a volcano like Shasta, the question is not whether magma exists below the mountain. The question is how much of it is melt, how much is stored as crystal-rich mush, and how those zones interact when fresh magma arrives from depth. That distinction between melt, mush, and frozen rock is central to the current reading of the volcano. A pocket may be a localized lens of partial melt, a reservoir where crystals and liquid coexist, or a staging zone where magma is temporarily held before moving upward. The term can sound simple, but the geology is not. The Mount Shasta studies point towards storage in the mid-crust, with additional evolution in the upper crust before eruption, and the regional Cascades work suggests similar storage depths beneath many arc volcanoes. Taken together, the evidence argues for a transcrustal system, not a single chamber at one neat depth. That is the part of the Mount Shasta story that matters most right now. Not that a dramatic change is underway, because the USGS monitoring record does not show that. Not that one isolated image has solved the mountain's plumbing, because the newer regional seismic work itself notes limits at Shasta. The important point is that scientists now have enough pieces to say the volcano is built on a layered magmatic architecture, one that has likely stored and moved melt at several levels over time. More detailed imaging, denser monitoring, and continued geochemical work will decide how many pockets are really there and how they connect. By the end of that work, Mount Shasta may look less like a single reservoir hidden under one mountain, and more like a stacked system of pathways, temporary stalls, and melt-rich zones that have been active for a very long time. That is not a conclusion about eruption timing. It is a description of the geology now coming into focus, and it is the reason the volcano remains one of the most closely watched in California. The picture that is forming beneath Mount Shasta becomes clearer when the different strands of evidence are placed side by side rather than viewed in isolation. The chemical record preserved in erupted rocks indicates that magma does not move in a single uninterrupted surge from depth to the surface. Instead, it pauses, evolves, and mixes in stages, leaving behind signatures that point to storage at multiple levels within the crust. When that record is aligned with seismic imaging across the Cascade arc, which highlights zones of reduced wave velocity between roughly 5 and 15 kilometers, or about 3 to 9 miles, the implication is consistent. The crust beneath the volcano is not empty space between eruptions, but an active framework that can hold melt in more than one place at once. That framework is not static. One of the more significant implications of the Mount Shasta studies is the role of time in shaping the system. Melt can reside in the crust for extended periods, cooling and crystallizing into a partially solidified state, often described as a crystal-rich mush. Within that mush, pockets of liquid magma can persist, reactivated when new material rises from deeper levels. This means that what might appear as separate pockets are not always isolated bodies. They can be connected intermittently, forming pathways that open and close depending on pressure, temperature, and the rate of magma supply from below. The system behaves less like a tank and more like a network that reorganizes itself over time. Mount Shasta currently shows low seismicity and negligible deformation, a combination that suggests no immediate escalation toward eruption. That context becomes more meaningful when viewed alongside the concept of distributed storage. A volcano can contain melt without producing the kind of surface signals typically associated with imminent activity. In such cases, the magma remains contained within its storage zones, not yet moving in a coordinated way that would disturb the surrounding rock enough to register as significant earthquakes or measurable ground swelling. The absence of those signals does not contradict the presence of magma. It simply indicates that the system is not undergoing rapid change at present. At the same time, the presence of multiple storage levels introduces a more complex set of conditions that scientists must track. Movement at one depth does not always translate immediately to movement at another. A recharge event in the deeper crust, for example, may take years to influence the shallower regions where eruptions are typically initiated. The 2022 Mount Shasta study suggested that some magma can ascend from around 15 kilometers, or about 9 miles, to the surface in a matter of years, but that ascent is often preceded by mixing and storage at intermediate depths. This layered progression means that early signs of change could begin deep below the volcano, long before any surface indicators become apparent. The broader Cascade's data strengthens that interpretation by showing that Mount Shasta is not unique in this regard. Many volcanoes in the arc appear to share similar depth ranges for magma storage, even if the exact geometry differs from one system to another. This regional consistency supports the idea that subduction-related volcanoes commonly develop transcrustal magmatic systems where melt is distributed across multiple levels rather than confined to a single chamber. In practical terms, this shifts how volcanic behavior is understood. Instead of waiting for one reservoir to fill and erupt, scientists consider how different parts of the system interact, how pressure is transferred, and how melt moves between zones. Mount Shasta's long eruptive history provides additional context for interpreting this structure. Over tens of thousands of years, the volcano has produced a wide range of eruptive materials, from fluid lava flows to more explosive deposits. That diversity is consistent with a system where magma evolves in stages, changing composition as it resides in different parts of the crust. Each stage of storage and mixing leaves its mark, creating a record that reflects not just the end of an eruption, but the sequence of processes that led to it. The presence of multiple magma pockets fits naturally into this history, offering a mechanism for how such variation can develop over time. What makes Mount Shasta particularly important in this context is its classification as a high-threat volcano, combined with its current state of relative quiet. This contrast underscores the difference between hazard and activity. The hazard is defined by what the volcano is capable of producing, based on its history and structure. The activity is defined by what it is doing now. A volcano can have a high hazard potential even when it is not showing signs of unrest, especially if its interior retains the ability to store and mobilize magma across multiple depths. As research continues, the focus is likely to move toward refining the picture of these subsurface connections. Improved seismic coverage, more detailed geochemical analysis, and advances in imaging techniques may help resolve the boundaries between different magma pockets and clarify how they interact. Each new dataset adds resolution, turning broad inferences into more precise maps of the volcanic system. For Mount Shasta, that process is ongoing, with each study contributing another layer of detail to a structure that is already understood to be complex. The emerging view is not one of a dormant mountain hiding a single reservoir, but of an active geological system maintaining a network of storage zones beneath its surface. These zones may remain stable for long periods, but they also retain the capacity to change, driven by processes that operate far below direct observation. Understanding how those processes unfold and how multiple magma pockets behave within that framework remains central to interpreting the future behavior of one of the most prominent volcanoes in the Cascade Range.